Welcome, astronomers. This is our lesson for our fourth day, really our third instructional day. With this, you should be viewing this lesson on Monday of our second week of school. And this is the asynchronous lesson. Of course, if you're a first period astronomy, you should be joining me for the live or synchronous Zoom session over this topic. And the topic you can see right here on the PowerPoint is apparent and absolute magnitude. And this is our last lesson for sort of the first half of Unit 1, where we're taking some time to learn about the night sky and just sort of those basics of astronomy. All right, so I'm going to cut my video and let us proceed so you can see everything that's on the screen. All right, so apparent and absolute magnitude. The word magnitude here is something that if you've taken physics, that term might be familiar. In this context, it doesn't necessarily mean exactly the same thing as what we would mean in physics, where it just means the amount of a measurement. For example, like, how quickly an object is moving, like, 10 meters per second. The value of 10 meters per second is the magnitude of the measurement versus its direction. But here, magnitude is itself a term for a kind of measurement. And that is the brightness of a star, typically a star. It could be something else too, like a planet, comet, asteroid, whatever. Anything that we can see in the night sky that's bright and large enough to reflect light, or if it's producing its own light as a star would. So the reason why the word magnitude is selected here is because it comes from the Latin word for great. So larger magnitude represents a greater brightness of the star. That's kind of how you can interpret it. So how bright the stars appear to us, in other words, our perception of the star, if you literally walk outside at night and you're looking at a star or a planet, this perception we have of the brightness is called apparent magnitude, because that's how bright it appears to us. And you'll notice it's symbolized with a lowercase m. And this is how we describe star brightness based on what we can see with our own eyes, or simpler telescopes, usually refracting telescopes, maybe some reflectors as well. Another word for it, sort of, is flux. You should start to associate those two terms together, apparent magnitude and flux. And one word for that is because it can fluctuate or change over time, especially for some stars more than others. How bright a star actually is, as if you could see it a little more up close, not too close as to be a problem, but much closer than we are from most of the stars of the sky. This is what we call absolute magnitude. And again, you'll notice it's symbolized with a capital M. And this is also referred to as luminosity, which we're going to spend a fair amount of time this year talking about that. That's a very important type of measurement for stars. This is another way to talk about luminosity. So again, just like how we should associate the terms apparent magnitude and flux, we should also associate the two terms absolute magnitude and luminosity. So we sort of have these two pairs of terms. Both kinds of magnitude are measured on the same magnitude scale. And actually, it works in reverse. And again, I kind of misled you a moment ago where I said greater magnitude means a brighter star. In terms of actually scaling it, it's a little bit backwards from that than what you would expect. So smaller numbers and even negative numbers indicate brighter stars. And larger numbers, positive larger numbers, indicate dimmer stars. And also notice that there is no unit of measurement. So again, if you have some familiarity with physics or chemistry where you're talking about units of measurement, again, like I mentioned, meters per second as a unit of speed, you don't have anything like that here. And there's some mathematical reasons behind that. We don't really have to worry about that for this course. But what you do want to understand is that the scale here for magnitude is also not, it's not as straightforward in terms of how much it can increase or decrease by. And what I mean is, again, like if we go back to speed for a moment, if you compared two objects, one moving at 5 meters per second, one moving at 10 meters per second, you would expect the 10 meter per second object to be moving twice as fast as the 5 meter per second object, because 10 is twice as great as 5. On the magnitude scale, though, every number on the scale is not just 1 times larger than the previous number. Instead, like it says here, each magnitude on the scale is 2.5 times dimmer than the preceding number in increasing order. So here's an example of what we mean. Magnitude 2, notice that it's positive 2, it's not negative 2. That would be different. Magnitude 2 is 2.5 times dimmer than magnitude 1, but magnitude 3 is 2.5 times 2.5, or in other words, 6.25 times dimmer than magnitude 1. So you actually get, even just the first handful of values, positive values, going up from 0. 1 to 2 to 3 to 4 to 5 to 6 and so on. Even just the first 10 numbers, you start to get very quickly to very dim stars. In fact, some of the dimmest stars that we can possibly see with our own eyes without telescopes or anything are around magnitude 5 or 6. So you very quickly reach a limit of what's visible to the naked human eye. All right, and here we just have some different diagrams showing the magnitude scale, comparing the magnitudes of some different sky objects and things like that. I like this one in particular because, again, we mentioned that small numbers, but especially negative numbers, are going to represent brighter objects. So when it comes to apparent magnitude, which again is how we see things, obviously the brightest sky object is the sun, and it is bright enough that its magnitude, its apparent magnitude, is negative 26.8. So, and don't forget, again, each magnitude number is 2.5 times dimmer, at least when we're going positive, than the previous number. So if we're going into more negative values, that means each one is 2.5 times brighter than the lesser negative value. So for something to have a magnitude of negative 26.8, it's going to be much, 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 much brighter than anything else in the night sky, even something with a value of -2 or -1.7 or whatever. Again, the moon, of course, is the next brightest sky object, the full moon especially, because that's when we see the most of its surface. And at its brightest, it appears to be about -12.5 magnitude. Venus is the third brightest night sky object, and it doesn't crack the top 10, if you will. It's still stuck at about -4.4. And again, don't forget, Venus is a planet. You know, it's not a star, although sometimes it's given a nickname of the morning and the evening star. So when we dial down from Venus, we finally get to an actual star, and this is the brightest star of the night sky, and that is Sirius, and it's at -1.5 for its magnitude. There is no star, of course, other than the sun, that has a larger apparent magnitude than Sirius. And again, notice I'm focusing on apparent magnitude right now. Alpha Centauri, which is one of our closer stars, it's right at about 0. Vega is another good indicator for a magnitude of close to 0. So still very bright, but now we've exited the realm of negative values for magnitude. Betelgeuse is a very bright star. It's in the top 10 brightest stars. It's about 0.8, so it's positive, but still a very low value. It's less than 1. Polaris, the North Star, at about 2.5. Again, like I mentioned, the limit for what you can see with your naked eye is about 6. Barnard's star here is at 9.5, and the reason why it's mentioned is because it's a relatively close star as well, but it's a red dwarf, so it's very dim. So even though it's closer than some of these other stars, we can't see it with our own naked eyes. You need either a powerful infrared telescope or a powerful optical telescope. And again, like you can see, the more powerful telescope you can get your hands on, like Hubble, Keck, things like that, you can be able to view much, much more dimmer night sky objects, up to a magnitude of about 30. And again, don't forget, that's not just 30 times dimmer than a magnitude of 0. It's 30 times, or you have to multiply 2.5 times 2.5, 30 different times to get how many times dimmer that would be. All right, so a little more about apparent magnitude. So again, let's say we're out viewing the night sky. We're looking at two different stars, star A and star B, excuse me. And star A appears to be much brighter. And why could this be? And there's a couple of different reasons why, a couple of different possible explanations. The first one is simply distance. Star A may not actually be inherently brighter, have a greater magnitude, that's another way of saying that, than star B. It may simply be closer to us. On the other hand, another thing, it might be size. Star A and star B might be close to to each other in temperature, but star A, if it's bigger, it will still be inherently brighter. So this is a case where the actual luminosity of star A would be greater. And also possibility 3 is tied to that as well. It says temperature and energy output. Star A is hotter and releases more light. So that's just a if it produces more energy from its core, and sometimes that would also result in it being a different color as well. And we'll learn later on in the year that, say, for example, bluer stars are hotter than redder stars, for instance. That's another possibility here. All right, so how do we correct for the possibility that star B might actually be brighter if we could see it up close? And we do that by using something called absolute magnitude, which again, we already introduced, but we need to kind of get into the details of it. So with absolute magnitude, and again, we already said it's tied to the concept of luminosity, the true brightness of a star. Basically, what we do is we imagine that all stars are the same distance away. So if we could take all the stars that we can see in the night sky and put them all at the same distance, and if we set that distance at 10 parsecs, which again, don't forget, a parsec is equal to about 3.26 light years. So 10 parsecs is about 32.6 light years. If we could do that with all the stars and compare their brightnesses all at the same distance, then we get to where we come up with these absolute magnitude figures. If we use the factually incorrect model of the celestial sphere to help us figure out the true brightness of a star, that's kind of what we're doing here. Because don't forget, with the celestial sphere idea, we kind of just suppose, like the ancients did, that all the stars were more or less at the same distance on a fixed plane, or again, sphere around the Earth. And we kind of make that assumption to make the absolute magnitude measurement possible. Now, another thing to mention here, we have this concept or this formula called the distance modulus formula. And it can be used to calculate absolute magnitude, again, capital M, that's the variable, based on the apparent magnitude and the distance to the star. Now, on the other hand, you can also use this formula to calculate the distance, and that's something we're going to revisit later in the year. So, but if you know the distance to the star, and there's a few different methods of trying to find that, we're going to be spending, like I said, a lot of time on that. And if you know the apparent magnitude, which is value m, lowercase m, excuse me, then you can rearrange this formula to calculate for our our absolute magnitude right here. All right, so again, luminosity is tied to absolute magnitude, so let's take a little more time to talk about luminosity itself. Again, it's the actual brightness of a star, and what it really measures is how much light it releases. And it depends on a couple of factors, primarily the temperature of the star and the size of the star. If either or both factors are high, then the star is going to have a high luminosity. And both factors are ultimately controlled by the mass of the star. Again, that's a big concept that we're going to talk about later on the road in the spring of the semester, or the spring semester of the year, excuse me. We measure the size of a star as the radius, so how far it is from the center of the star to the surface. And we measure it in units called solar units. And we can measure it in other ways. We can measure it in kilometers or something. That you do see that. But the easiest way to compare luminosities and radii and all that of other stars to each other is with these solar units. And what we mean by a solar unit is we look at these different measurements for the sun and set that as the standard. So for example, one solar radius is the radius of the sun itself. And we can do the same thing again with temperature and luminosity. So for example, the surface temperature of the sun is one solar unit of temperature. The luminosity of the sun is one solar unit of luminosity. And so again, we can use this as a model of comparison. So if I say that a star has 3 solar radii, that means it is 3 times as large as the sun. If I say a star has 15 units of solar luminosity, then it is 15 times brighter than the sun, and so on. And you can see some other comparisons here. Now, because radius and temperature are the 2 factors that affect luminosity, we can formulate this mathematically. The formula itself is pretty simple. It says that L luminosity is equal to radius squared times temperature to the 4th power. And so if you know the radius and you know the temperature, you can just calculate those exponents and then multiply the 2 values together, and you'll know the luminosity. But again, when you're using this formula, you would need to make sure that all three measurements are being measured in solar units. If you, for example, if you start using radii measured in kilometers and temperature in solar units, that would not give you the correct value for luminosity. We will be calculating with this later in the year, and we'll only ever use solar units, so there won't be any confusion between different kinds of units and so on. All right, a little more about luminosity. The diagram on the right shows that very different stars can have the same luminosity, since luminosity is related to both radius and temperature. For example, small hot stars like this little blue star here can be equally as bright as large cooler stars. Again, we mentioned a few minutes ago that bluer stars tend to be hotter. They produce or emit higher frequency energy waves, electromagnetic energy waves. Whereas redder stars, which red stars are interesting because they can come in both very, very, very large or very, very small varieties. But if they're a large red star, then that red color indicates that they're relatively cool. They would not be as hot as the sun, for instance, although their large size means that they're still going to be emitting a lot of light just because it's a large surface to emit energy from. One other thing here is that the diagram below also shows how these different factors can relate. Just don't forget that, again, apparent brightness equals apparent magnitude, and luminosity equals absolute magnitude. And again, apparent brightness, another term we said for that was flux. All right, a little more about absolute magnitude. We mentioned that it's the brightness at the assumed distance of 10 parsecs from a star. And again, it uses the same scale as apparent magnitude, where, like we mentioned, lower numbers, especially negative numbers, represent brighter stars than higher numbers. And again, absolute magnitude compares luminosity, not perceived brightness, true brightness of the star, not how it appears to us. Now, with this in mind, the sun has, again, an apparent magnitude of negative 26.74, which again is really, really bright, brightest thing in the sky. But if we look at its absolute magnitude, it ranks at a positive 4.83, which again is not really, really bright. Like we said, if the sun was actually in the night sky at a distance from us at 10 parsecs, then it would be one of the dimmer, less standout stars of the night sky if it were 10 parsecs away. And you can see that here on this scale. We have, for the bottom part is apparent magnitude, and the sun is all the way to the left, again, past negative 26. Whereas on the top part for absolute magnitude, it's all the way to the right, which tops out at about positive 4.5 or so. Now, again, we mentioned Vega a few minutes ago. It's got very little variation in its the comparison between its absolute and its apparent magnitudes. Its apparent magnitude, I mentioned, is close to zero. It's about 0.03, whereas its absolute magnitude is only a little bit higher at 0.582. So there's, how Vega appears to us in the night sky and how it would appear to us at a distance of 10 parsecs would not be incredibly different. It's fairly consistent. And that also indicates to you that Vega is at a distance already that's kind of close to 10 parsecs. Sirius also would be kind of another example of that. It doesn't have a huge variation either. All right, one other diagram I have for you here, or a set of little images. I like this one because this kind of gets back to what we were talking about in terms of true brightness versus distance. And for example, in this image here with these two silver cars, car A's headlights appear brighter than car B, even though both cars are identical and therefore they have the same brightness from their headlights. And so the reason why car A appears brighter is because it's closer to us, car B is farther back in the distance. Now, on the other hand, over here we have car A, this time as a red truck, car B is still the same silver car from before. And it says that they're at the same distance, but car A's headlights appear brighter, and that's because on this truck model, it uses a brighter pair of headlights than car B does, the silver car. And again, down here, similarly with stars, if an observer sees two stars and star A appears brighter than star B, it can be because star A is literally closer to the observer than star B is. And so this little oval here, that shows you what this observer would see. star A would appear larger and brighter than star B, simply because it's closer. Even though if you actually look, star B, if we consider its luminosity or absolute magnitude, it would actually be the brighter star, even though the observer does not see it that way. Actually, this is the last little image. I really like this one. This shows you the Canis Major constellation, which is home to the star Sirius, the brightest star of the night sky. And it shows you, again, how Sirius and its companion stars of that constellation look to us in the night sky. But if we could shift, again, everything to that standard distance of 10 parsecs that we use for absolute magnitude, this constellation of Canis Major will look totally different. And Sirius would actually be one of the least noticeable stars in that constellation. We could still see it, but a lot of the other stars near the rear end of Canis Major here would be much brighter, including the tip of his tail. Even his front paw would be a much brighter star than Sirius would be. So that's a cool little comparison. I like that one a lot. And again, I actually misspoke earlier in the lesson. This is actually not our last night sky lesson. We still have to look at our lesson on the top 20 brightest stars and Bayer designations. But we're close. That will be the last one. So thanks for joining me today. That's all we have to look at for apparent and absolute magnitude.